So now it's on. Is that right? So yes, I believe it is recording now. Yeah, so whenever you have an isolated system where you just have two particles coming in, they collide and they bounce back, all the forces in this problem, are internal. In other words, these two particles together form a system, and during the collision, particle 1 will exert a force on particle 2, and particle 2 will exert an equal and opposite force back on particle 1. Both of those forces are internal to the system. There isn't an overall external force acting on the system. And in that situation, we showed that the total momentum of the system is conserved. That is, if you take the sum of the momentum of particle 1 here, plus the vector momentum of particle 2 here, if you add them up, that will give you the total initial momentum of this system before the collision. And that has to equal the total momentum of the system after the collision. So if I were to write this out in more detail, for particle 1, the momentum will be its mass m1 times its v1 initial, whatever its initial velocity was, plus m2, v2 initial. That is the total momentum of the initial system, of the system initially. That has to equal m1 v1 final. This is the velocity of particle 1 after the collision, plus m2 v2 final. So that is a statement of momentum conservation, which we derived in the last class. Any questions about that? And again, even for situations where it's not quite true that there are no external forces, for example, if you have a midair collision of two things, then in principle, there is the force of gravity that is external to the system. It's acting on both of the particles. But again, in that situation, what we can do is we can analyze the system just before the collision and just after the collision. And during that, we can ignore gravity because during the collision itself, the collision forces are so much bigger than the external force of gravity that it's essentially negligible. So we can therefore still use momentum conservation. So what will happen is if two midair particles collide, the total momentum just before the collision will be equal to the total momentum just after the collision. But after the collision happens, then they will go off in different arcs, and their momentum will not be conserved because gravity is acting on both of them. So they will start to accelerate under gravity and stuff like that. But just for that moment of right before collision and right after collision, we can assume momentum is conserved. Any questions on that? So let's look at a particular example. And this is something that we're all kind of intuitively familiar with. We know that if you fire a bow and an arrow or something like that, you will experience a recoil, right? Even if you fire like a rifle or something like that, then when you shoot, you will experience a backwards recoil. That is a result of the conservation of momentum. So here is a problem that we'll kind of go through carefully. So here we are told that there's this archer, and he's standing on frictionless ice. So therefore, we can ignore any forces of friction. And then this archer will fire an arrow. The arrow is going to go off to the right. We know from our intuition what's going to happen is that the archer is going to slide back. He's going to start sliding back because he will experience a recoil velocity. So in this problem, what we're going to do is we're going to actually calculate what is that recoil velocity. And we will understand a lot of the physics. So for example, we will see that if this archer's mass is very large, the recoil velocity will be very small. If the mass of this archer is very small, the recoil velocity will be very big. All those kinds of intuitive things we will uncover. So here's some details. We are told that the total mass of this archer, the bow and arrow, plus the quiver of arrows that he's carrying, whatever set of arrows he has, all of that together, we are told, is 60 kilograms. Then we are told that this archer fires an arrow, and this one arrow has a mass that is 0.03 kilograms. And when he fires this arrow, it goes off horizontally to the right with a speed of 50 meters per second. So the question then is, what is the subsequent velocity on the ice of this archer after he fires this arrow? So that is what we are going to try and uncover. So let's apply here the principle of the conservation of momentum. And by the way, I'll just make a little editorial comment here based on reading some of your tests, is that especially when you're working on the final exam and stuff like that, try to lay out the logic of what you are doing by writing symbolic equations. There was a tendency to just, like here's problem A, and it was just like 0.3 over 7 equals whatever. And then that was like the solution. And often the solution of that was wrong, and I'm in no position to give you any credit for that because you're not demonstrating an understanding of the concepts. So you have to kind of demonstrate that in your writing. So I'll sort of pay extra attention to how we can do it in this particular problem, for example. And then we'll see how that works. So the first thing we will do is we will identify some information that's given to us. So let me write down and collect some information. We are told that the, let's first draw a picture. We are told here that initially, this is the frictionless surface. We have here the archer plus all the arrows together. I'm going to break them up into two pieces. I'm going to call one of them M1, and then I'm going to call the other one M2. M2 is going to be the mass of the arrow that he fires. So I'll say here M2 is 0.0300 kilograms. That's this information here. So what's going to happen is that initially the archer and the arrow, they're both just sitting there. He has not yet fired the arrow. So they're both just sitting there. So the mass of the arrow is 0.303 kilograms. Therefore, the mass of everything else that's going to recoil against this arrow, we'll call that M1. And what is that going to be? Well, that's going to be the full 60 kilograms minus the mass of that one arrow. All right, so I'm going to go here and say that, let me move this down a bit. So I'll come here with 60 kilograms minus 0.03 kilograms. What is that? 59 point, is it 59.97? 59.97 kilograms. Someone double check that. And so this here is the initial situation. And in this initial situation, what are we told? They're both at rest. So I will say here that V1 initial is 0. Let me pick my positive x direction to the right. I'll say that's my positive x. So V1 initial is 0 and V2 initial is also 0. Because everyone is just sitting there. He has not yet fired the arrow. Let me throw this out as a question. That's not a top hat, but anyone can chime in. What is the total initial momentum of this system? Anyone? 0, right? Because this object M1 has 0 initial velocity, which means it has 0 initial momentum, m times velocity. And M2 also has 0 velocity, therefore, it also has 0 momentum. So the total initial momentum of the system is 0. Now, when this archer fires the arrow, notice again, we are using the conservation of momentum. And so therefore, the final momentum, whatever that is also going to have to be 0, right? So now let's look at what is happening in the final situation. So in the final situation, right after he fires the arrow, we're going to have a situation where M2, let me draw this a little bit. This is M2. It's now going to go to the right with some velocity V2 final, and M1 and this is M1, it's going to be moving in this direction with some V1 final. And what are we told in this problem? Again, the positive x is to the right. We are told that V2 final is 50 meters per second. Right? The arrow is fired with a speed of 50 meters per second to the right. And the question we are asked to find is, what is V1 final? This is the thing that we need to figure out. What is the recoil velocity of the archer? Any questions on that? So again, think in a test, this is how you would set up the problem. I can give you so much partial credit if you set up information like this, even if you get completely the wrong answer. You've drawn a diagram, you've collected the information. Next, what we will do is we will introduce the concept that we're going to use. We are going to use the concept of the conservation of momentum. Which says that the total initial momentum has to equal the total final momentum. So this is a symbolic equation that is expressing the concept that you're using. The total initial momentum is equal to the total final momentum. That would be worth points, for example. Then I break it up a little bit more. I say the total initial momentum is the initial momentum of particle 1 plus the initial momentum of particle 2 has to equal the final momentum of particle 1 plus the final momentum of particle 2. I can then write more symbolic things. What is the initial momentum for particle 1? It's M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. And then I look up here, I see that the initial velocities are all 0. And so therefore we end up with just this is 0, this is 0. And then if I just apply in the x direction, then I will end up here with 0 is equal to M1 V1 final. So this is momentum conservation in x direction. Because remember, again, momentum conservation is a vector statement. Momentum is conserved along x direction. So here I will have 0 is equal to M1 V1 final plus M2 V2 final. Any questions on that? So what I'm going to do is, now that we have come here, I'm going to make it into a top hat question and see if you can now solve for what is V1 final using the conservation of momentum. And in particular, in top hat, I'll ask you for the magnitude of V1F. Is V1F going to be positive or negative, you think? It's going to be negative because the recoil is going to be in the negative x direction, given that we have identified the positive x direction to the right. The recoil is going to be in this direction. It's going to be a negative answer, but in top hat, I will ask you to just put the magnitude of that velocity. So let's switch to top hat. Before we do that, any questions about this? So the goal of the top hat question is to use this setup so far to figure out what is the numerical value of the recoil speed of the archer. All right, so let's go here. So for the problem being discussed, calculate the magnitude of the recoil velocity. So don't put a minus sign, it's just asking for the magnitude. And then we'll. There it goes. Okay. Let me add a timer. Yeah, don't put a negative sign. It's just asking. Yeah, it's asking just for the magnitude. All right. Do people need more time? All right, let's see what we got. All right, looks like most people got it. Some people put minus signs. I was asking for the magnitude. Some people are just putting random things. Okay. All right, so let's go through this carefully. So here we want to solve for V1 final. So therefore, I will get that M1 V1 final will be equal to minus M2 V2 final. Right? And then I can divide both sides by M1, and I'll get that V1 final is minus M2 over M1 V2 final. Any questions about that? Did people have issues with the algebra? And so now I can go ahead and plug in the numbers. V1 final is negative. M2 is 0.03 kilograms. M1 is 59.97 kilograms. And V2 final is 50 meters per second. And I think if you plug in those numbers, so notice first off that the kilograms cancel here, and you're left with units of meters per second, as you should for velocity. And I think if you plug in the numbers here, you get that V1 final is negative 0.0250 meters per second. Somebody double check me on that. So that's what so we have used the conservation of momentum to figure out what is the recoil velocity for this archer. Okay, so here's the answer. And in some sense, the physics is, we can look at the physics in this solution here. You can see that the recoil velocity here depends on the velocity with which the arrow went out, and then it's weighted by the ratio of the masses. So here, this is the mass of the arrow, m2, and then this is the mass of everything else that's recoiling against that arrow. And so if the mass of everything else recoiling against the arrow is very big, then this number becomes very small. The recoil velocity is very small, whereas if m1 is very small, then the recoil velocity will be very big. That makes sense. Any questions on that? And so again, I'll just say that on a final exam or something like that, this is kind of how you should try to think about writing solutions, where again, at the in the problem, the least interesting thing to me is that it's 0.0250. I really don't care about that. What I care is that you understand the concepts and what is being used to get at the answer. Any questions on that? And so in the top hat question, we just asked what was the magnitude of this velocity, which is like the speed of the recoil. And so therefore, we dropped the minus sign. So if you're ever in a bow and arrow situation, or you're in a firing range, or you're shooting rifles or something like that, just know that, you know, if you have a big recoil or something, you don't have to feel bad. It's just physics. It's just determined by the ratio of your mass to the mass of the bullet that's going out, for example. So, all right. So there's a part B to this problem, which let me kind of, it's just a slightly more complicated situation, but essentially the same thing. So I'll go over it relatively quickly. It says he then fires a second identical arrow at the same speed relative to the ground, but now at an angle of 30 degrees above the horizontal. So instead of shooting the second arrow straight out, he's now shooting it at some angle above. What is his new recoil speed? Okay, so let me, in the interest of time, not go through it in detail, but just kind of walk you through it. So again, we have the same situation, except that now this archer is already moving with some recoil speed, right, before he fires the second arrow. So the first arrow has gone off to the right, and this entire system is now moving to the left with some recoil velocity of minus 0.250. And then, as this whole system is moving to the left, this archer will fire the second arrow, which is the second box. And this second box is going to go off in some direction like this. And then this archer is going to recoil even more after firing off this second arrow. So in this situation, here, this is your initial situation before he fires the second arrow. And this here is your final situation before after he fires the second arrow. So now if I ask you, what is the initial momentum of the system? Well, the initial momentum of the system is the momentum of this whole thing. So the mass, so the initial momentum here along the x direction, so just let's focus on the initial momentum just along the x axis. The initial momentum is the mass of all of this, which is 59.97 kilograms, because that first arrow went out. And we know that the whole thing is moving with a recoil velocity of minus 0.025 meters per second. So this mass times this velocity is the initial momentum of this system along the x direction. What that means is that after the second arrow is fired, the total momentum along the x direction must still be exactly the same as this total initial momentum along the x direction. Is that clear to everyone? So that first part, the total initial momentum was 0 because they were both at rest, and then he fired an arrow. In the second part, they were already moving with some recoil velocity, and then he fires a second arrow. So now the initial momentum is this. Now let's look at the final momentum after he fires the arrow, but just let's look at the x component of it. Just the x component of it. And what we want to figure out is what is the recoil velocity on the ground of this archer after he fires a second arrow. Well, after he fires the second arrow, the mass of this will be the total initial mass, which was 59.97 kilograms, minus the mass of this second arrow, right? So that's the mass of this guy right here, times the x component of this final velocity of this guy right here. So this here is like the m1 v1 final of this guy right here along the x direction. Any questions on that? Now, what about the second arrow? We were also told that the second arrow is also fired with a speed of 50 meters per second, but at an angle of 30 degrees. So the momentum of this along the x direction, well, is its mass, which is 0.03 kilograms. But now its velocity is 50 meters per second along this direction. But what we are interested in is only the x component of the momentum, which is 50 times cosine of 30 degrees meters per second. Right, is the x component of this guy right here, where this angle is 30, is 50 times cosine of 30. So that is the x component of the momentum of this arrow. Any questions on that? And so now all I have to do is do this. Set P1 initial x equal to P initial in the x direction is equal to P final in the x direction for the total system. So that means this guy here has to equal this entire thing. And we want to solve for this variable, which is V1 final x, the x component of the velocity of the archer. So setting these two equal to each other, we can then solve for this guy right here. After some algebra, you will find that this is the result. And now the new velocity is minus 0.0467. So you see that this archer has now picked up even more speed after firing the second arrow. Any questions on that? Okay. All right. Let me just go. Okay, so as I said in chapter 6, we're going to be focusing on collisions, and it is useful to classify collisions into two types, elastic collisions and inelastic collisions. So again, imagine two things coming at each other, colliding, and we will classify them into either elastic collisions or inelastic collisions. First, let me give you the definition of each. An elastic collision is a collision in which the total momentum of the system and the total kinetic energy of the system is conserved. So in an elastic collision, what happens is two particles come in, they collide, and they go off. Initially, the total system has some initial momentum, and it has some total initial kinetic energy. Kinetic energy of particle 1 plus kinetic energy of particle 2. Both of those quantities are conserved. So the total momentum before the collision is equal to the total momentum after the collision, and the total kinetic energy before the collision is equal to the total kinetic energy after the collision. In inelastic collisions, we have still the conservation of momentum, but kinetic energy is not conserved in inelastic collisions. So here is an example of an inelastic collision. So when these two cars collide, the reason that they're an inelastic collision, because you can see in the collision, a lot of the energy went into deforming the metal and producing heat and starting fires somewhere. So a lot of the initial kinetic energy of the two cars before the collision is now transformed into other types of energy. So the kinetic energy is no longer conserved. I think there was a Facebook meme going around somewhere where you could, like, in principle, cook a chicken by colliding two cars hard enough, producing enough heat, and or frying an omelet or something like that. So that you're converting the kinetic energy of the cars into frying an omelet. So in that case, kinetic energy is not conserved. but momentum is conserved. So if you keep track of all the little bits of particles before the collision, and then they break up into various bits after the collision, you keep track of the momentum of each one of them, momentum will still be conserved. All right. So I think maybe this is a good stopping point for me here. Let's see, there's a question in the chat. How hard do I need to punch a chicken to cook it? Yeah, that is a good question. The kinetic, yeah. Energy, when something is at a certain temperature, the average kinetic energy of the molecules in there is about 3/2 kT. K is Boltzmann's constant. You need some thermodynamics for that. Anyway, let me go ahead and stop the recording.